Good morning, good afternoon, and good evening, everyone. Welcome to the Actuarial Technology Summit 2024. This is a presentation about actuarial models and IT, the past, the present, and the future. Just some words about myself. So I'm Pierre Mier. I'm both an actuary and an IT developer. I've always been passionate about IT development for actuaries, and I designed over 10 software in my different experiences as Ernst Young, Actuaries, Willis Watson, Wyatt, Adactis, and today Milliman. So let's go with this presentation and start with the past. So what I suggest is to make a parallel evolution of IT and actuarial science, because as actuaries, we like to look at the past to try to predict the future. So obviously, this is only a summary here. I just mentioned the main steps of the history, in my opinion, but of course, it's much deeper than that. For example, it all started, in fact, in Babylon, 4000 before Christ, with the first attempt to quantify risk. But what was first written was by Demosthenes, 4th century before Christ. It was the first non-life insurance. It was a cargo insurance. In parallel, there were some attempts to build the first calculators. So this was more for spatial calculation. And the very known one is the Antikythera mechanism, which was designed first before Christ. It is a very complex mechanism that we have still difficulties today to understand exactly what it does. So in a recent movie, some of you know this mechanism as a time-traveling machine. Obviously, this is not that. It's more an astrologic mechanism, very complex, that we could only solve with the help of artificial intelligence. So this brings us from the beginning of our presentation to the end of the presentation, where we'll talk about artificial intelligence. Then, when we move on actuarial science side, 2nd century after day, there is a first life table, which is the Ulpian life table. It is a little bit different from the one we know, but it is the real first attempt to draw a life table. So back to the antiquity. In my opinion, the world slept through centuries, so nothing much happened before we arrive to the 17th century. And here, same person, both advanced on the IT side and the actuarial side. It's Blaise Pascal. So Blaise Pascal created the first real calculator. It is a mechanical calculator called the Pascaline. And at the same time, with Pierre de Fermat, they have founded the probability theory. So they released the first books about probability theory as we know it today. Also, at the same period, there were the first insurance organizations, especially following the fire in London. A lot of insurance companies were created to prevent it, like, for example, even in Germany, the Hamburger Feuerkasse, which is maybe the first life insurer as we know it today, was designed after the Hamburger people saw what happened in London during the London fire. Then obviously there is also the Lloyd's, and Lloyd's about non-life insurance, and still, as was the case with Demosthenes, insuring boats, floats. Also, the first mortality table was derived at this same moment by John Grant and Edmund Halley. They just visited graves and noted the date of birth, date of death of everyone in London graveyards, and this enabled them to issue the first real mortality table, same as we know today. Then, if we move to the 18th century, there is Basile Bouchon and Joseph-Marie Jacquard, who built the first programmable loom, so sewing machines. The first one was Basile Bouchon, in fact, but it was programmable with a tissue, so it was not super, how to say, reliable. So Joseph-Marie Jacquard had the idea to use tabulating cards, which are much more reliable, and that were used for quite a while because it was used for over 2 centuries. At the same time, there was the first real-life insurance companies built on actuarial principles, with the first actuary as we know it today. So we could say maybe the first actuary, real actuary, is Richard Price, who worked for Equitable Life, and they wrote books of actuarial science at this moment. Then, in 1837, there was a first analytical machine which was digital. So it was still just a calculator, but digital, and it was designed by Charles Babbage. And Charles Babbage met with a genius in mathematics. She was 17-year-old, I believe, when they met only. And he asked Ada Lovelace, hey, could you put some algorithms in my machine? Charles Babbage had already the idea to use a tabulating card within its analytical machine, but Ada Lovelace was really the first to say, hey, but this could be used for so much more, for more algorithms. And we can consider Ada Lovelace was the first IT developer. Then in 1896, there was the foundation of the tabulating company. So they used tabulating cards to do some, to count the number of inhabitants and do some stats in the US especially. This tabulating company is today very well known because it has changed name and became IBM. In 1895, the International Actuarial Association was created, where its first form, but a Comité Permanent des Actuaires was created because actuaries realized that they needed to meet worldwide to discuss actuarial techniques, exchange, and make the actuarial science evolve all together. So this is something quite not new, 1895. Okay, let's move to the next century. So you certainly have heard about Enigma, a crypting machine which was incredible, built by the Germans in 1919, and that was only cracked by Alan Turing during World War II. So 1942, Alan Turing could crack this machine. Alan Turing, by the way, at the same time issued the first version of what would be the basis of all programming languages, which is ALGOL. We'll come back to this later. Then 1920, this is my personal finding. Maybe it was even earlier, but I've read in a book from 1920 the first chain ladder as we know it today. It was really formalized and known as chain ladder by when Henry wrote about it in 1938, but I have really seen the exact same method already in a book of insurance from 1920. So chain ladder, still very popular today for non-life insurance reserving, is clearly not new. Well, if we move a little bit forward, in the 1940s there were the first computers, but they were quite basic, or they were analogic. Analogic computers were quite interesting because they were not binary, so they could program much more variety in just one calculation cycle. But the problem is that they were not super reliable. I mean, it was good for physics valuation and very performant, more than computers based on binary code. But they were progressively abandoned because with binary machines we had more precise results, even if they were slower. So the first real big machine and really performing one was again designed by IBM in 1952. It was a 16 kilohertz machine with 18 bits, and 16 kilohertz for this moment was a lot. It's 16,000 operations per second, which was absolutely crazy. At the same time, there was a big advance on the actual side with the copula theory, which was derived by Maurice René Fréchet in 1951. And these copulas, we consider it really breaking new in actuarial science. We only really use it since the early 2000s. But to be honest, it's not new. It was from 1951. In 1957, the actuaries, during their international gathering, ICA, which happens today every 4 years, so it's still happening today, but this year was special because they realized actuarial science cannot evolve without IT. And this is the second time since Blaise Pascal that IT and actuarial science really join again together. And actuaries started to program on these big machines like the IBM one from this moment. Then big years for programming language. Okay, ALGOL was invented by Alan Turing, at least the concepts in the 1940s. But then two very big languages emerged between 1969 and 1972. It's Pascal and C. Pascal and C are the ancestors of most languages we know today. At the same time, there was a big advance in theory and artificial intelligence. It is the invention of GLM as we know it today and still use it today. Today, GLM is used for most pricing exercises in the insurance industry. GLM is a particular case of a neural network. So we can consider that it's the first use of artificial intelligence in insurance. And GLM, again, are still used today. Okay, if we move forward, then 1972 in actual science there was Born-Ferguson, which is an evolution of Schneider. If you take Schneider and Born-Ferguson, these are the methods used today by over 80% of the reserving methods by insurance companies all over the world. We have made a report in 2016 at the International Actuarial Association, and in particular the ASTIN section, that mentions that, Schneider and Born-Ferguson are really the must in non-life reserving. Schneider, 1920. Born-Ferguson, 1972. Not new. Black and Scholes, which is the basis of a lot of calculations in asset side equities, was invented in 1973. Still used today. Then a big change for computing. Two companies, so still IBM on one side and Apple on the other side. I would say also Commodore, but fortunately Commodore did bad choice in the 80s, so it's not here anymore. But let's say the two biggest were Apple and IBM. They have released the first personal computer, and it was an absolute revolution for everyone, as personal computers maybe, but also for the business. So in 1981, 1982, okay, we started to have computers. So three big inventions were done. Maybe one of the biggest is Internet, which has been an absolute revolution. But also Excel has been invented at this moment. So the ability to write models very easily by a visual interface equals this cell plus this cell. It was invented at this time. And also C++, which is a very good language for performance, we'll get back to that, was invented at this moment. Then two other languages, several other languages were created at this moment, but two in particular. Python was created in 1989 and R in 1993. In 1990s, also the first actuarial software were created. Why is that? It's because Excel was not sufficient performance-wise to run models, actual models. So you needed to code, but coding for actuaries was not easy, and especially C++ is not easy at all. So several consulting firms, actual consulting firms, or IT companies decided to create the first live solutions, what we call low-code solutions, meaning that the actuaries don't have to code everything in C++. Most of the code is already coded by this application, but they have to write just a part of the actual formula, release this part in C++. So it's quite easy in the end, and we call it low-code. And this software, I can name them, are Prophet, Moses, and G-Alpha. All were born at the same time. Okay, 1993 also an actual method which is quite a reference today. It's a Mac method. So trying to start stochastics in non-life reserving. And obviously this is still used today. Okay, let's move to the next slide. What happens next? So the first is maybe Deep Blue or Deeper Blue versus Kasparov match. So the first AI against the world champion Garry Kasparov, a great chess player. Deep Blue, in fact, lost the match, but then IBM came back with an evoluted version, even more performing, which was called Deeper Blue, and Deeper Blue won the match. Okay, there is some how to say controversy about this, but still, Deeper Blue maybe was not absolutely better than Kasparov, but at least very close to it. And there is even a series you can watch on the TV at the moment that will tell you this story. This is the beginning of a revolution, but this revolution will really come 20 years later. Anyway, 2000, another very good language was developed, which is called C#. C# was a memory-safe language and very performing with a very good object architecture, and it was designed by Anders Hirschberg. Anders, I have not talked too much about it because this is just a summary here, but Anders Hirschberg has been an absolute asset all the way on the programming languages. He was the author of Turbo Pascal, which was Revolutions, and Delphi, which was an absolute success, a very, very good language for the new systems. Then C#, and then he was in the 2010s the author also of TypeScript, which is a fantastic evolution of JavaScript, and today has been recognized as the best language for internet. So it has replaced JavaScript, for example, in React, which is one of the best languages for doing performing front-end and net applications. Angular, the other, the competitor of React, there are several, Vue.js also, but and several others. But Angular, for example, was only based on TypeScript by this same guy. So, okay, Anders Hirschberg released C# in 2000. Then, in 2001, we managed to decode the full DNA sequence. It was the Apollo project, and the cost to decode the full DNA sequence of a human body was 2.7 billion euros. I will get back to that. 2006, the first new regulatory regime based really on risk, and not the first version, which was a little bit basic based on volumes, was released. So it was the Swiss solvency test, so obviously for the Swiss market. It was based on the Solvency II principles, but Solvency II was a European project and it took very, very long to finalize it. So Solvency II was in force in Europe only 10 years later. So the first regulatory regime based on the risk was 2006. 2007, a revolution on the IT side, the iPhones. Today, smartphones are a big revolution for all of us, as you know. In terms of IT, I would also mentioned Julia was created in 2012. Why this language? In fact, the problem was the interpreted language, which were easier to code, were slow. But the fast languages are considered too complex. Okay, maybe C# is okay, but for non-IT, they wanted something a little bit simpler to use. So Julia was created with this target, and we'll get back to that later. Then 2015 also, so I mentioned Solvency II, the regulatory regime for insurers was in place in 2016. The China version of Solvency II was in place since 2015. Same year, a revolution in IT science. Alpha by DeepMind. Alpha built an artificial intelligence which learned Go and chess and has beaten everyone. I mean, okay, Deep Blue was same level as Kasparov in 1998, approximately. Alpha chess really crushed any chess champion, but even it crushed all the computers that would crush the world chess champions. So it is an absolute incredible evolution, and I believe Alpha chess learned chess in about 3 to 4 hours to become this crazy good artificial intelligence that revolutionizes chess theory. And regarding AlphaGo, never a computer managed to beat the Go champion, world champion, because it's Go, you have to go very, very far until you know if the line you have chosen is good or wrong. So in terms of IT power, it was impossible if we project everything to really understand if the position was good or not. So computers were not so good at Go at all. But AlphaGo, we don't know how, but it crushed it. Maybe just a reference to DNA. The cost to decode a full DNA sequence in 2018 was only 750 euros. This is crazy because the cost in 2001 was 2.7 billion euros. So the computer performance was much increased, but also the algorithms were much improved. Then 2018 to 2023, there is a company which was created by Elon Musk and some others, but Elon Musk left the company just after. It has released the first real artificial intelligence usable by everyone. So it was first GPT-1, today the one we know, GPT-4, which is the one you would mostly use when you use ChatGPT, was created at this moment. And that's a revolution, and we will talk about that later. The same moment, Actuarial Science 2023, IFRS 17, from 2020, and it's still not finished, there is the ICS monitoring, so the attempt worldwide to have a globalized and standardized regulatory regime based on risk valuation. Maybe I could mention that very recently, GPT-4 is used with a variation. It's what we call the AI computer use. So in fact, the AI can take control of your computer and do tasks for you. We'll also talk about this later. Okay, so this is the history. Where are we now and where are we going next? I would maybe mention before switching to this that the actual science, the actual needs have evolved through the years. We have mentioned this, and we need more and more computing power. That was not such a big issue because the evolution of our needs followed a little bit the evolution of the computer performance. There is this Moore law that specifies that the number of transistors in a dense integrated circuit doubles approximately every 2 years. If I make it simple, every 2 years the power of computer doubles, the memory also for the same price doubles, the memory that we can have, the RAM, the live memory. So it was a true law, and this is incredible because we are here with something exponential. It was true until the beginning of the 2010s. And why is that? It's because the size of the transistors have been reduced so much that we are close to the atomic scale and we have big heating problems. So we cannot continue this law anymore, so we had to derive some new ideas in order to continue to follow the needs, the demand for more and more performance. So, okay, where are we today? The actual modeling challenges. First of all, it is pricing. We need to price products. And for this, more and more, we use artificial intelligence. So it was GLM, as I mentioned before, but it's switching to some new algorithms today. We have predictive analytics. Artificial intelligence is used to make some selection or adverse selection, etc. We also need more and more power for our model for enterprise risk management. Especially ALM is very demanding, but DFA, the stochastic version of it, is even more demanding. Business planning is fine, generally, even for ORSAs, which is the regulatory version of the business planning. We are okay with just one simulation, so it could be okay. But ALM, DFA, no, it's not so easy. Computers do not deliver enough performance, so we have to find ways to optimize this. There is also reinsurance in this area and risk control and diversification. Also, we need IT for prudential regulations, as I mentioned. So we have CROS, ICS, internal models, ORSA, Solvency 2, SST, risk-based capital in the US. And also, new accounting standards become more and more demanding. IFRS 17 in particular has been a revolution and is demanding more and more computing power if you really want to make the exact valuations. Today, what do we use for that as actuaries? This is a survey that was performed by Milliman in 2022, mostly in Europe and Asia, India. US was not in this survey, I believe, but the results could be similar. What are the two main tools used for your models? This was the question asked to actuaries within insurance companies. No surprise, Excel is still one of the big winners. Why is that? Actuaries are really fluent in Excel. Excel is a genius thing for developing design models. It's visual, as I said before, you make equals this cell plus this cell. It's so easy to track formula. So it's the most agile solution, and you can be very productive with it. But the problem is that it has no detail of teamwork. It has poor reliability. And you need VBA code because Excel is only bidimensional rows and columns. It's not enough for your model. So you need to, for example, loop through policies, loop through stochastic simulations, loop through scenarios. And for this, you need VBA code. And once you have VBA code, you have black boxes and slow run times. There was also a study performed by Ray Panko in the US in financial and insurance area. And the result is that errors in spreadsheets are pandemic. On all Excel models studied that were used in production, over 88% of these models contained at least one error. It's not one or two, it's 88% of the models that contain at least one error. Why is that? It's because Excel is prone to error, because used in production, maybe you forget from one quarter to the other to increase the size of a range, or you don't have a real debug functionality. So anyway, this is the reason why it's not only Excel. I mentioned specialized software designed in the early 1990s, like again Prophet, Moses, MG Alpha for life, or in non-life like Emblem or Adaptive Modeling or such software. I'm not making an exhaustive list here. Anyway, these software are powerful and with OD12, but there is still a specific knowledge required. You need to learn them. It's long and costly to develop, but we'll get back to that. Why specialized software is good, And at the same time, some companies, and especially in Europe and Asia, are stopping them and trying to think, what is a good solution for us? So maybe the last option, which is in-house development, really developing on C#, on Python. It can be powerful, I'll get back to that, but actuaries are not IT coders. It must be coded from scratch, and it's costly and hard to maintain. Again, we'll get back to this because this is an important point. And as I mentioned, some insurers in Europe and Asia have switched from low-code solutions to in-house development. Here you have some players who have recently switched. To be honest, Allianz, one of the biggest, maybe the biggest company worldwide today, always used in-house development. They use Java, especially from 2005. So the rest of the market, the biggest one, are moving to C# or Python. And why do they make this change? Because this change is very, very costly. So why making it? So we have asked the market, and what we have heard is lack of reactivity of the software provider, or lack of independence in the modeling, lack of agility for the coding and the models, lack of performance, low ability to automate, and also the costs are sometimes an issue. Okay, so these are for actuarial challenges. Let's see about computational challenges. So again, as I said, we have an issue with IT, with miniaturization of components, of transistors. They come to too close from the atomic scale. So we cannot do as we did before. We made an attempt. Maybe you heard about hyper-threading, which is the idea of you take one core, one processor if you want, and instead of making it one processor, it is two processors virtually. It means that the same processor makes as if it were two processors. This led to some issues of security, because then two processors could access each other, physical data. So it led to Riddle and Zombie and some other big security issues. So Jensen Huang in January 2019 in CES mentions that the Moore's law, which I discussed about, which predicts the regular increase in the computing power of silicon chips, is dead. And how do we do? We need more and more computing power as actuaries. But well, when did we go wrong? Let's just take this example. In 1969, we sent men to the moon. And the computer was called the Apollo Guidance Computer, was using 72 kilobits of memory with a processor which was 0.043 megahertz. Today, a simple iPhone is over 1 million times more powerful than this incredible computer that was used in 1969. And we need this power to display what? A page of text? This is crazy. We need an amazing amount of performance for very simple applications today. If you take the number of lines of code, HGC lines of code were under 150,000. Today, when we see Facebook, it's over 50 million lines of code. Google is over 2 billion lines of code. Well, cannot we do things better? Do we need so much performance? Cannot we optimize? Because before, with less, we did more. Let's take an example here. Basically, in fact, when we build algorithms as actuaries, we can really optimize a lot the performance. Let's take a very basic example. Sorting a list is something which is of complexity like quadratic complexity. If you take a size of list which is 1 million, it can take 2.8 hours for, in a computer, I have not put the references here, but 2.8 hours to do this, for example, sorting. Optimal sorting, you can go to another complexity, which is n log of n, not n square, and then it becomes 0.06 seconds instead of 2.8 hours for 1 million size of elements. So, I mean, just by optimizing our algorithms, we can switch from something absolutely crazy like 316 years of calculation time. If you take an algorithm of the factorial complexity and you are with n equal 50, you need 10 power 48 years of calculations for the same computer. I mean, it's absolutely crazy, of course. So it will not be the IT evolution and the increase of performance that will solve our issues here. It is, okay, isn't there a way to make our algorithm of a lesser complexity, going from a level of complexity n squared to n log of n, or even n, if possible? And these are the questions actuaries have to ask themselves today, because they need more power, but power is not infinite. And so we need absolutely to find the most optimized algorithms. Before I come to the performance of different programming languages, I will talk here about the most popular programming languages as of today. So as I mentioned, Python was created in 1989. It was absolutely not popular at the beginning. And yet, today, it became the most popular. Why is that? It's because it's completely free. It's one of the reasons. It's free. And for universities in particular, having something free is easier because sometimes there is problems of financing, I don't know. But having something free, and even if the cost of the software needed to run a C# is not high, I mean, still, Python is free. That's a reason. Another reason is that it is easy to code when you have no IT language. Quite easy. It's still a language. It's still a programming language. For example, it's untyped. So it has been a success. But you know, what is a success once is not necessarily a success in the future. Let's take the example. The programming language of the year 2005 was Java. And Java this year was the most popular. And as I mentioned before, a lot of people thought, okay, we need to put all our models, actual models, in Java because this is the language of the future. But Java did not end being the most popular. In 2012, in fact, in actuarial science, I don't speak generally in IT science, but in actuarial science, R was the most popular to do some programming for actuaries. Still because it's free and quite easy, even if it's command lines, to be honest, not a big fan personally. But okay, it had a success. And we thought, okay, R is the language of the future. Well, in 2018, the programming language of the year, it's based on the TIOB index, you can see the reference on the PowerPoint, was Python. And Python became the language of choice of most insurance companies worldwide, except for performance reasons. Some of them switched to C#, and good choice for performance, and I will get back to that later. In 2024, is Python still the most popular? The programming language of the year will be, in my opinion, of course it's not decided. In 2023 it was C#. I don't believe it will be C# in 2024, maybe, but it will be a battle otherwise between Python, Java, and Rust. So, in fact, a language, apparently, if we look at the past, has a duration of being the most popular, and then it might be changed. So we should not invest too much in one particular programming language. Especially there is one language which is only 28th in ranking at the moment. It's Julia. I mentioned it before. And this programming language, Julia, is coming stronger and stronger for actuaries. As I said, because it has the simplicity of Python, but with the performance of C#. Okay, but let's talk about performance. Before that, I would just like to mention even old languages which were once very popular, like Fortran. Fortran was completely forgotten, like switching to the 29th place. But today we realize its performance for some types of jobs is amazing. So it came back to the 10th place. We are seeing really a cycle for programming languages. And it's difficult to project which one to choose for the future. But then let's look at the performance, because we mentioned we have performance issue. So which is the most performant language? And for this, I base myself. This is a reference paper by a university center of research in Portugal, I believe in Porto. So you have the reference paper here. So they used for measuring energy consumption Intel's running average power limit, RAPL tool, which was already proven in several papers. You have the references here. The RAM used was measured using profilers, and they used the algorithms of the computer language benchmark games. So this is a set of algorithms which represent all the types of complexities that we can find in mathematics. Okay, so all these algorithms have been launched 10 times with a cooldown of 2 minutes between each run, and in always the same machine. So the obtained results are the following. In green, you have the compiled language. In blue, based on virtual machines, and in orange here, you have the interpreted languages. If we look at the average of time or consumption, energy consumption, the average of compiled language is 120 joules. For VM-based programming language, around 500. For interpreted, 2,400. So it's much more than compiled languages. And if you look at the performance, the runtime, if the compiled languages are referenced, the VM-based ones are 4 times slower and 17 times the interpreted. If we look at the ranking, even between C and Python, Python is the most popular today. The energy in C was 57 joules. With Python, 4,604. I mean, the difference is absolutely huge. If you want to consume less energy today, coding in Python is certainly not a good idea. Okay, there are ways to optimize Python. We'll discuss that, but Python, if you code like normally, is 75 times more consuming energy than C. If you look at the runtime, it's nearly similar. You want runtime? Okay, then choose C, because Python, you have 70 times more runtime than C, 70 times slower. If you look at others, C# is approximately, which is much easier to code, is approximately 3 times slower than C, but still 24 times approximately faster than Python. And Julia is in the same range. So Julia, maybe the easiness of Python, the speed of C#, not so bad a choice. And if you look at RAM, it's a little bit different. Then Python becomes quite good. Julia is not so good. You need a lot of RAM because it's just-in-time compilation. It requires a lot of data structure. Anyway, so it is more memory used, but still, I believe it is acceptable. C# here does a little bit better. Okay, so these are the results. But is the choice so obvious? We'll get back to it. Let's talk about the future. What do we do? What do we choose? So first of all, is Moore's law really forever dead? To be honest, maybe not. There is ongoing research on GPUs. GPUs, well, it is a trend. It was a trend. It's less and less a trend. in my opinion, but GPUs is a way to access more processors, more cores, at a cheap cost. Problem of GPU is that there is limited memory exchange between the different cores. It's not at all easy to make memory exchange, so if you need a model with a lot of interactions, it's not so easy, and also the set of instructions is restricted, which causes some other issues. Okay, but this is still a way you can follow. You can have more GPUs. You can have molecular DNA spintronic transistors, or we are even talking about quantum computing, which, okay, they say is a potential infinite power source. The first one was derived by IBM, but today I believe in China they have made some very good advance on this too. So still IBM is on the scene. It was from the 19th century. But another solution is just to go to the cloud, because the cloud becomes more and more a source for infinite capacity computing. Yet there is an energy consumption, so this is a question to be asked. Maybe just a remark, quantum computing, is it something so new? In fact, quantum computing is, in a way, using several states, like it's not binary anymore, but it's using several states. It's a little bit, there's some analogy with the analog computers that we had in the 1940s. So it is maybe a coming back to something that's already existing. Of course, much evolved, and we believe with more precise calculations, so solving the issues that we had on analogic computers. There is another point. I said, yeah, C, C++, fantastic for performance. Ooh, but maybe not so good for security. There is this paper which was released by the White House that say you should not use C or C++. You should avoid absolutely C and C++. Why is that? It's because C and C++ are not what we call memory-safe language. I mean, the memory is not locked to the current process. I won't go too much into the detail. Is it really an issue? Yeah, let's look at some stats about it. Microsoft mentioned that 70% of security issues come from memory safety issues. That's huge. For Apple, it's even 80%. For Google Android, it's even over 90% of security issues coming from memory safety issues. So, White House said, okay, this is a good language, but we should avoid this non-memory safe. And they listed the following safe languages: Rust, Go, C#, Java, Swift, JavaScript, Ruby, Python, Delphi, Object Pascal, and Ada. So this is our recommendation. Obviously, Julia is also a safe one, so this could be in the list. Python, I said, yeah, Python is not performant, but you can improve it. It's true. For example, the library NumPy of Python, which is a vectory matrix-based library, a little bit like MATLAB. With this, you have very good performance, very close to C and C++. Why is that? It's because this library is based on C and C++. It was compiled in C and C++. So don't we have here the memory safety issues? So yes, we can improve the performance, but then we have to use non-memory safe languages. When do we have a NumPy version compiled in Rust and not in C, C++? This can come. Python is evolving. Maybe it will get better. It will certainly get better, and at least it will get to the average range of interpreted language. The performance that we have in this study is really too bad, even for an interpreted language. But okay, the future will tell. Then we have asked actuaries that moved from low-code solutions to C# or Python. We have asked them 2 years after, are you satisfied about it? If you ask the same actuaries just when they released the model in C# and Python and finally managed it, they will all tell you, yeah, we are very satisfied. But the question here was asked 2 years later, to the bosses of the actual modeling departments. What about performance? For C#, everyone is very satisfied. There is no discussion. Maybe C# is 3 times slower than C, C++, but it's still super, super, super fast. So people are very satisfied. Python, oh my God, it's slow. Why is that? I mean, we've seen that obviously, but then what they have done is that to reach the desired performance, they have put either GPU or big cloud use, and then to reach the desired performance, and it's cumbersome and it's costly. And so this is about performance. Who develops? For C#, the problem is that it's mostly IT that design. It's too much an IT language. So actuaries, in this case, mostly release specs and check the result. But then there is a lack of agility. Each time you need a new version of the model, you need to build this IT actuaries team. Python is developed by actuaries. That's a big win, because they both release the specs and code. It's so much easier, so much more agile. So it provides more autonomy, but still there is a peer review needed, because it is still a programming language. It's not like it's Excel. It's not that easy to peer review and to validate. About new version releases, as I mentioned, so it's very complicated in C#. In Python, it's still quite complicated, and there is an issue in Python. If the person who designs the code is leaving the company, then it's quite complicated to maintain. About code clarity, to be honest, C#, very, very IT language, so it's considered as a complete black box by actuaries. There is an Excel replication needed. In Python, it's complicated to read, and it's not a black box, so it's better, but still you need to replicate the calculations in Excel if you really want to understand them. And then there is a new trend, and this trend started in 2017. It's called no-code solution of very low-code solutions. What is it exactly? In fact, the idea is, okay, the best language to design models is Excel, so why not keeping this language? Yeah, but we don't want VBA, so we need to find a solution to avoid VBA, and there are some other issues, so we cannot just do that. So okay, it's just the model design which is in Excel, and sometimes it's with extensions to make Excel be able to handle more stuff like SQL type things or stochastic things. For example, Excel does not have the capabilities of OR in terms of distribution, so you need some specific add-ins that are provided by no-code providers. So this is step one. Excel is a language to design the models, and then we code 2 to 4 times faster than Python, Julia, or C#. And then we convert it to C# and C++ because we need performance. We need the model to become big. We need the model to loop on all the policies, to loop on all the scenarios. We cannot do that by VBA. So we convert it to a programming language. C, C++, not safe. So maybe C# is the best option. And then it's not only reproducing the Excel calculations, but it's converting automatically by some AI the models into multi-dimensional models. So you can really have the performance and the no limit of the cloud. And then you set up the production process, you automate and you integrate. So as it's in the cloud, you have full elasticity in the calculations. You can set up workflows like the former low-code solutions were providing, audit trail, sign-off, integration with APIs. So in the end, you have the best of all worlds with these no-code solutions. And to be honest, since 2017, I believe I've seen over 1 new no-code solution proposed to actuaries, mostly proposed by US and Europe, main countries in Europe, maybe UK, and obviously Milliman Mine, which I'm involved in, is based in France, but designed and released in the US. About AI and LLM, to conclude this talk, it is a revolution. what is it used really today in insurance for? The real use today is for underwriting, especially CRM and claims management. LLM helps so much. It assists in finding which claim is a fraud and etc. So this is where it is really used, but it could be used by actuaries. And there is a paper that I've referenced here, which is amazing, that that tells you how you can benefit as an actuary from AI and LLM. First of all, it can be a coding assistant. I'll get back to that in the next slide. Can help you for problem solving. I don't know how to do this. How do I do it? In a way, so it can also be an educational tool. It helps for drafting reports or summarizing reports. It's very good for this. And it's good for data preparation. It's cleaning. To follow the regulatory changes, it can really help you, because reading all the regulatory changes sometimes can take a while, can generate documentation. And to be honest, it's quite new, but you can even have the LLM take control, the AI take control of the computers, of your computer, and work for you on your computers. So you have the link here. You can have a look. So is it really working? Well, it mostly works, except it does a lot of mistakes, but I'll get back to that later. And this kind of solution was used to solve some modeling issues. And what is funny is that at the moment, it really reproduces the behavior of the human using the computer. And at the moment, it was solving a complex issue, and the artificial intelligence decided to browse to look at Yellowstone images, pages, while it was working, just to, it just reproduced the human brain, but yeah, it can have quite a strange behavior. So, for example, as a coding assistant, let's use AI LLM GPT-4. We tested on 2 languages, Excel and Python, 2 reference languages. And we have 2 kind of stuff. Let's do a bootstrap in non-life reserving, or let's program a typical life model. So in bootstrap, in Excel, the result was amazing, except it was wrong. It was difficult to notice, but some of the indices used were wrong and not referencing the good self. In Python, we asked for bootstrap, but it just mixed up with the standard chain leader. No, this is not what we want. We want bootstrapping, so we want stochastic. Then it applied a normal distribution to loss development factors. Is this bootstrapping? Definitely not. So the answer was really wrong. Life projection, it was generally okay, but very basic. It corresponded to a very simple case, so it needed to be rewritten and tailored. And a problem with Python is sometimes it used packages, reference packages that even do not exist. So maybe found it somewhere in the web, but a protected page, or I don't know, but these packages did not exist. So it was quite not usable. So some recommendations: double check each line of code written, whether it's in Excel, whether it's in Python. The written code is often not optimized and can result in slow run times. And for code completion or bug solving, rather use GitHub Copilot. Copilot can be quite amazing. Just type the beginning of the row that you want to write. It understands what you want to do, and it will propose the whole end of your function that you are writing. It's amazing. Try that. Amazing. I really recommend trying GitHub's Copilot. So globally, using LLM can save time, but is risky. The actuaries can be incentivized to overtrust the written code, and we have to be careful with that. And we can tend to use it as a black box. We have to be even more careful with that. We have to master the algorithms applied, otherwise we could do something completely different. The conclusion of the paper, as I was mentioning, is why LLMs will not fundamentally change the way actuaries work. It can still enhance the work of actuaries and of the insurance industry. So this is for my talk. We are now coming to the question and answer, and I will be pleased to answer any question you may have on any part of this presentation. Thank you for your attention.